Here we have a large circle and a small circle that's tangent to the large circle at this point. From this point, we draw a line here that intersects the small circle at this point, and then we draw the tangent line at this point to the small circle, like this, and then we connect these points like that and these points like that. We need to show that this angle equals this angle. First of all, take a look at the segments. We know that they're parallel to one another, because if we consider homotity with this center that sends the small circle into the large circle, then this point would go here, this point would go here, and so this line would go to this line, which means that they are parallel. Homotity sends a line to a parallel line. Because of this cyclic quadrilateral, we have that this angle corresponds to this arc, and so it equals this angle. Because of this line parallel to this line, we have that this angle equals this angle. And because of alternate segments theorem applied for this triangle and this circle, we have a tangent line here, and so this angle corresponds to this arc, which corresponds to this angle, and so these two angles are equal. And therefore here we have an angle bisector. Now this triangle, it has this as a circumcircle and an angle bisector. They intersect here, and so this point must lie on the perpendicular bisector of this side. And of course we can say the same thing about this triangle here, in which we have a circumcircle and an angle bisector, and they must intersect on a point that lies on the perpendicular bisector of this side. From this cyclic quadrilateral, we know that this angle equals this angle, then this angle equals this angle, and because they are equal, we know that this triangle is isosceles. And similarly, from this cyclic quadrilateral, we know that this angle equals this angle, and this angle equals this angle. And because these two are originally equal, then this triangle must be isosceles. And so this side equals this side, and this side equals this side. Another thing we can notice is that since this angle equals this angle, then this triangle is similar to this triangle. After all, this angle is common in both triangles, and also this angle equals this angle. In other words, the circumcircle of this triangle is tangent to this blue line here, because from the alternate segments theorem, we have that this angle equals this angle. And so we have that this squared equals this times this. You can think of it in terms of the similar triangles here and here, or you can think of it as the power of this point with respect to the circumcircle of this triangle, which on the one hand is this squared, and on the other hand is this times this. And similarly, we have that this squared is this times this. Now let's see what happens to this construction when the circles are externally tangent instead of internally tangent. This here is a random line passing through the point of tangency of the two circles, and then from here we take a tangent line to this circle, and it intersects the other circle at these 2 points. And then we take this red line and this red line here, and we also take this and this segments. So where is the angle bisector now? Turns out that this time it is an external angle bisector of this triangle here with the 2 red sides and this as a base. And now this is an external bisector of this angle. To prove this, let's first notice that this line is parallel to this line here. Because of a homotity that transforms the small circle into the large circle, this point goes here, and this point goes here, and so this line goes to this line, and so they're parallel. Now, we know that this angle equals this angle. We also know from the alternate segments theorem that this angle equals this angle because they both correspond to this arc, and this is a tangent line, of course. And we know because of this line is parallel to this line that this angle equals this angle. Next, this is a cyclic quadrilateral. We know that this angle corresponds to this arc, and so it equals this angle here. Finally, because of the same cyclic quadrilateral here, we have that this angle equals this angle, because the sum of this and this is 180, and the sum of this and this is also 180. And here we have it. This angle equals this angle, and so this is an angle bisector, external angle bisector of this angle. We have even more equal angles in this picture. For example, from this cyclic quadrilateral here, we know that this angle equals this angle, and also that this angle is 180 minus this, which equals this angle. And so we have that this triangle is isosceles, because this angle equals this angle. And we also have that this triangle here is isosceles, which we could also see by considering this triangle, where the external bisector of one of the angles intersects its circumcircle. And the same thing goes for this small triangle here, because this is the external bisector and this is its circumcircle, and so their intersection is here on the perpendicular bisector of this segment. There's even more to this construction. Notice that this angle here equals this angle because of the alternate segments theorem. Both correspond to this arc here. And we know that because this line is parallel to this line, that this angle equals this angle. And from this circumcircle, we know that this angle equals this angle. And so we get some similar triangles here. This triangle is similar to this triangle because this angle equals this angle and they share this angle in common. Therefore, this squared equals this times this. Or in other words, the circumcircle of this triangle is tangent to this line at this point. This again follows from the alternate segments theorem and the fact that this angle equals this angle. And so from the power of this point with respect to the circumcircle of this triangle, we have that this square equals this times this. So you can think of it in terms of similar triangles or in terms of power of a point. And same thing goes for this triangle being similar to this triangle, again because this angle equals this angle. And so the power of this point with respect to this circumcircle of this triangle is this squared, which equals this times this. It's exactly the same thing, but this time the circumcircle of this triangle is tangent to this line here because this angle equals this angle. Now returning to this situation again where we have a triangle, and this time we know we have an angle bisector here which intersects the circumcircle at a point on the perpendicular bisector of this segment, and we construct a circle that passes through this point, and is tangent to this line. And now we prove that it's also tangent to the circle, the large circle, at this point. This is exactly the same problem as we solved before, but in the opposite direction. Here's one interesting way to solve it. From this cyclic quadrilateral, we have that this angle equals this angle, and this angle equals this angle. And from the alternate segments theorem applied to this triangle here, and this tangent line, we know that this angle equals this angle. And similarly, from the same theorem for this triangle, we have that this angle equals this angle. From here, it follows that this line is parallel to this line, and also this line is parallel to this line. Now, from the parallel lines, it follows that this angle equals this angle, and also that this angle equals this angle. Now, one way to finish the problem would be draw the tangent line of the large circle at this point here, like this, and of the small circle at this point again like this, and then prove they are the same line from the alternate segments theorem for this triangle and for this triangle. And so if they're the same line, then the centers of this circle and this circle would lie on the perpendicular line at this point to this common tangent line. But I'm going to propose a different way. We know that this triangle is similar to this triangle because of this line being parallel to this line. Therefore, there exists a homotity centered here that sends this point here and this point here. And so it sends this line to this line. And therefore, it sends the circumcircle of this triangle to the circumcircle of this triangle. Because it sends one triangle to the other, it must send the circumcircle of one to the circumcircle of the other. And therefore, the green circle gets sent to the large black circle. And the center of homotity here lies on both circles. Now, because the homotity sends one of the circles to the other, it must send the center of the first circle to the center of the other circle. And therefore, the two centers of the circles and the center of homotity lie on a straight line, which is only possible when one of the circles is tangent to the other. And the point of tangency is the center of homotity, which lies on both circles. This is the optional problem. We have a circle and two circles that intersect one another at this point and this point, and both circles are tangent to the large circles at this point and at this point respectively. We take this line, the line that connects the two intersection points of the blue circles, and we intersect it with the large circle here, and then we connect this point and this point by this segment, and this point and this point by this segment. They intersect the blue circles here and here. And we need to prove that this line, the line that connects this point and this point, so the dashed line, is tangent to both blue circles, so it's the common external tangent line for the two circles. Similarly, if we prove this, it would follow that if we extend this line, intersect it here, and then take this segment and this segment, intersect it with the two blue circles, then these two intersection points would give us the other external tangent line to the two circles. And here's the solution. Here I've constructed the tangent line to the large circle at this point, and I've connected these 2 points with the segment. We know from the alternate segments theorem that this angle equals this angle because both correspond to this arc of the large circle. We also know from the power of this point to the two small circles, we know that this times this equals this times this from the power with respect to this circle, and then this times this equals this times this when we consider the power of the same point with respect to this circle. And therefore, this times this equals this times this, which means that this quadrilateral here is cyclic. And because it's cyclic, we know that the sum of this angle and this angle is 180, and the sum of this angle and this angle is 180. Therefore, this angle equals this angle. And now that we know that this angle equals this angle, we can say that this line is parallel to this line. Now take a look at this situation here for a moment. We have a circle and a smaller circle tangent to it, and then this line that comes from the tangency point. And I've drawn the tangency line to this circle at this point, and the other tangent line to this circle at this point. Then these lines are parallel, because there's a homotity centered here that sends this point to this point. This homotity sends the small circle into the large circle, and therefore it sends this tangency line to this tangency line. It just scales this small picture to become like this larger picture, where this point remains fixed in place. And so this line goes to this line under homotity, but homotity preserves parallel lines. And so because one line is the image of the other, it means that the two lines are parallel. And so if I take this to be the line tangent to the large circle at this point, and this to be a line that passes through this point and is parallel to this line, so this line is parallel to this line, then this line would also be tangent to the small circle, because it would coincide with the other line we had before. Tangent to the small circle means that it's parallel to this line. And the same thing we have here. Here we have this small circle, this point of tangency with the large circle, and then this line being tangent to the large circle and parallel to this line, which passes through this point, means that this line is tangent to the small circle as well. And the same logic we can apply for the other circle and prove that this line is tangent to this circle here as well. And therefore, this is the common external tangent line of this circle and this circle.